In this module, we discuss good measurement practices with special emphasis on analytical methods validation. Analytical methods is just one element in a larger measurement system. So if we were to do justice to methods validation, understand it better, apply it better, it would help if we had the bigger picture. Also, inputs about how other industries are coping with the issue of measurement validity. We first start by understanding what is measurement. A measurement tells us about a property of something. It might tell us how heavy an object is, or how hot, or how long it is. A measurement gives a number to that property. Measurements are always made using an instrument of some kind, maybe a ruler, or stopwatch, weighing scales, thermometers. These are all measuring instruments. The result of a measurement is normally in two parts, a number and a unit of measurement. For example, how long is it? 2 meters. While talking about measurement, it would help if we also understand what is not a measurement. There are some processes that might seem to be measurements but are not. For example, comparing two pieces of string to see which is longer is not really a measurement. Counting manually is not normally viewed as a measurement. Of course, if you're using an instrument like a particle counter, then it certainly is a measurement. Often, even a test is not a measurement. Those so-called checks or tests that normally lead to a yes-no answer or a pass-fail result do not constitute measurement. Now, what do we see here? We have a process, and a process has an output. There is what we call a nominal value or the target value, and the upper specification limit and lower specification limit, and the actual item being produced. As long as it falls within that acceptable band, it is deemed to be acceptable. So we have a process and we have its output, and we now have to have a specification and a method to confirm that the output is acceptable. So we design what is called a measurement system. Now, whatever is coming out of the process has a certain value. It is called the true value. The true value may not be coinciding with the nominal value. If it does, good, but it may not. It may be anywhere within that acceptance band. But wherever it might be within that band, it has a certain real value called true value. Now it goes into what we call the measurement system. Now here we see there are 5 measurements taken, and there is a certain variability in that set of measurements. When it comes out from the measurement system, the value that is observed by the measurement system is plotted against the nominal value. And what we see here appears to be a magnification of the so-called variability or spread that was there in the true value set. The observed value set seems to have a slightly higher variability about it. What does it mean? It means that the measurement system we are using is magnifying or amplifying or adding to the variability that already exists in the process. So, the total variability that we have is equal to the actual variability or the true variability in the process plus the variability that is being contributed by the measurement process. In other words, the total observed variability is the sum of the true variability of the process, and added to it is the variability contributed by the measurement process. The question we'd like to ask is this measurement system that we are using valid, reliable, usable, adequate? And for that, the measure is the ratio of the variance contributed by the measurement system to the total observed variability. Now, if that ratio is, say, less than 10%, we may consider it an acceptable measurement system. If it is greater than 30%, we may consider it an unacceptable measurement system. And if it is between 10% to 30%, we may take a call depending on the risk to the patient, the risk level of that particular measurement. If it is a red risk, we may not consider it acceptable. If it is a yellow risk, we may say it's appropriate or acceptable for that particular measurement. Now, this is just an illustration. For example, 10% may be too high a value. You might like to say for all your red level measurements, your ratio shall be less than 3%. For your moderately critical, the value should be less than 7%. And for the low critical, the ratio may be as high as 15%. Whatever, you have to take the call. But for that, you must have some meaningful data available to estimate what is the variability coming from the measurement system and estimate the total variability as observed in the total system that comprises the inherent variability in the process itself plus what is added from the measurement system. This study is called measurement system analysis. Now let's see what it says. A measurement system analysis, abbreviated MSA, is a specially designed experiment that seeks to identify the components of variation in the measurement. Now, when we say experiment, it is not like the classic experiments we carry out in the physics laboratory or in the chemistry laboratory or even the microbiology laboratory. This is a statistician's experiment, and this really translates to multiple replicates of a particular process to be able to, for him, identify the factors. He uses the word factors, the influencing factors, to be able to identify whether a particular factor has an influence or does not have an influence, and whether two factors are mutually independent or dependent. And if they are dependent, are they dependent directly or inversely? These are all the issues that a statistician worries about. And to be able to ascertain that, determine that, he tells you to run that many replicates in that many different settings, in controlled conditions. And then he analyzes the data. Just as processes that produce a product may vary, the process of obtaining measurements and data may have variation and produce defects. A measurement system analysis evaluates the test method, measuring instruments, and the entire process of obtaining measurements to ensure the integrity of data used for analysis, usually quality analysis, and to understand the implication of measurement error for decisions made about a product or process. MSA is an important element of Six Sigma methodology and of other quality management systems, including QS 9000 and ISO 9000. MSA analyzes the collection of equipment, operations, procedures, software and personnel that affects the assignment of a number to a measurement characteristic. So let's have a quick look as to generally how do they go about, how do they proceed in this investigation. As in the case of all investigations, they look at the Ishikawa fishbone and the contributing elements, the 5 M's and the E. In other words, the materials, the manufacturing method, the machinery, the measurements, the manpower, and finally, what is loosely termed as environment. Please understand, environment does not necessarily mean temperature and RH. It also includes everything else in that particular measurement space. Now let us take an example where we have a measurement issue. We have, let us say, an OOS. And let us say the material that has been tested and the measurement made is on a raw material. Now, what could have caused this OOS? It could be a misunderstanding in the specifications between the supplier and the buyer. Or it could be differences in the test methods at the supplier's end and the buyer's end. Or it could be that the instrument used at the buyer's side and at the vendor's side are different. Or that either of them or both of them are not validated. Or that either of them or both of them are not calibrated. Or the analyst at one end or at the other end or both are not qualified or trained. There could be ever so many reasons. It could be that the manufacturer's manufacturing method is not validated. It could be because of the reagents used, either at the supplier's end or at the buyer's end, the standards used, the support that is required, most critical element, the support by management, either by the supplier or by the buyer. Management in terms of not just asking for a measurement, but supporting the measurements post. Now, management support is critical in terms of resources required, the analysts required, the quality of instruments required, the quality of calibration that is required, the periodicity of calibration that is required, the maintenance that is required, the quality of reference standards and reagents that is required. All this contributes to whether a measurement continues to be valid or not valid. One very critical element, for example, is the sample. How representative is the sample? You give a good sample, you get a good result or valid result on which you can take an informed decision. But you give a rotten sample, an unrepresentative sample, you get misleading results. So, is that sample representative? Is it random? Is it independent? In other words, if there are 10 items that could have been sampled, did all of them have an equal chance to be sampled? Now, sampling process, is that valid? The sampling implements, are they appropriate? Have they been cleaned? Have they been used properly? Have they been stored properly? The sampling environment. So all this contributes to the validity of the measurement. Now, assuming the sampling process was right, for example, it is a representative sample, it has been drawn independently, it is a randomly drawn sample, the sampling environment was appropriate, the sampling implements were appropriate, the sampler himself was trained and made no mistake. Is that all? Is that enough? Does the matter end there? How is the sample handled? How is the sample transported? How is the sample stored? For example, anybody in microbiology knows that if you have taken a sample of water to estimate the bioburden, the longer you delay, the greater the proliferation of microbes that are likely to occur. That within an hour, the number of colonies may double or even triple. So what are the storage conditions, handling conditions, transportation conditions? Are they to be just taken out, or is there a special enclosure in which they should be kept to ensure that the integrity of the sample is at no point of time ever compromised? On reaching the laboratory, a properly drawn sample, properly handled sample, has still got to undergo a process called sample preparation before it can be taken in for the measurement in the measurement system. So, the mistakes that could take place in sample preparation, the mistakes that could take place in sample injection. So, all these are also elements that are contributing to the measurement that is shown by the measurement system. And if these are not addressed, the value that is given to us by the measurement system could be invalid. In the context of other industries, they have what is called a gauge R&R study, or a gauge repeatability and reproducibility study, if the measurement is on a variable like the assay, potency, temperature, pressure, weight, whatever, any variable that can be measured. And if the measurement is on an attribute, the statistician opts for what is called a kappa study. Now, what is an attribute analysis, variance analysis of attributes? It is categorized item, categorical data. For example, now you have a rating of high, medium, low, or critical, moderately critical, low, or you say pass, fail. So anything, or on a rating scale, you say on a scale of 1 to 10, how much would you rate this? You say 5 or you say 7. So assessing this kind of measurement, the variability in the measurement system that is trying to measure attributes, is subjected to what is called the kappa study by the statisticians. Here, I'd like to amplify a little more, since we are doing methods validation and we are talking about measuring a variable. So the gauge R&R study is more relevant to us. So how do they do it? What are the things they look at? And what are their significances? And more importantly, what can we learn from here when we carry out our own analytical methods validation? Let's have a look. Now, to be able to understand how gauge R&R studies are carried out by other industries under the Six Sigma concept or the ISO 9000 or QS 9000 systems, it helps to first understand some basic terms. The same word could mean different things in the pharmaceutical methods validation context and in the gauge R&R ISO 9000 context. So what they're talking about accuracy. We also talk about accuracy. And in both cases, the meaning is the same. Accuracy is the closeness to the true value, the observed value and true value. How far are they apart? Accuracy is a reflection of that. Precision, they talk about repeatability and reproducibility. We also talk about precision, we also talk about repeatability and reproducibility, but there is a slight difference in the way they use the word repeatability and they use the word reproducibility. Now, they talk about something called sensitivity of a gauge and the discrimination of the gauge. They talk about something called bias and the stability and drift of a measurement system. Then they talk about linearity. We also talk about linearity. But are we talking about the same thing? We'll soon see. And finally, they talk about a study that encompasses other attributes called the attribute study. Now, what does that really mean? So let's begin with precision, and that is the two words used by them, repeatability and reproducibility. Now let's discuss precision. In the context of gauge R&R studies, there are two types of precision. One is referred to as repeatability and the other referred to as reproducibility. Now we also have repeatability and reproducibility mentioned in the ICHQ2. We'll discuss that when we do methods validation. But there's a very big difference between the way what they mean by repeatability, what they mean by reproducibility, and what gauge R&R analysts are talking about. Repeatability in the gauge R&R context is holding all other elements controlled, that is, the environment, the analyst is the same, the gauge is the same, and the gauge conducts quickly under those control conditions a series of measurements. And the idea is to try and see if that gauge is able to give the same results that are in mutual agreement, and how close are the results on repeated measurements using the same item and the same analyst in the same laboratory at around the same time. This is a controlled experiment. The idea is purely to determine the repeated measurements from the same gauge by the same analyst in the same environment in quick succession. Are the readings in mutual agreement? How close are those readings in terms of their agreement? Here the focus is not to try and see whether the average value of these repeated measurements is matching with the true value or not matching with the true value. That is a separate study. Here the focus is purely to establish the consistency of the gauge, of the instrument. So what we call instrument repeatability is what they refer to as repeatability. Now, in the case of reproducibility, it is not under controlled conditions. It is under what is called operating conditions, where anything can vary. It could be morning, it could be afternoon, it could be evening. It could be analyst A, it could be analyst B, it could be analyst C. It could be summer, it could be winter, it could be monsoon. Now, how close are those readings? How well do they agree with each other? What is the level of mutual agreement? What is the level of consistency? That is reproducibility in the gauge R&R context. In other words, repeatability is purely instrument repeatability, and reproducibility is about the ability to produce readings in close agreement, taking all factors except the instrument into account. All other elements may vary. Now they have a concept called bias. Now what is bias? Technically, it would be the difference between the mean observed value and the true value. Now, this is given to you pictorially. The picture on the top left shows tremendous consistency that shows high precision, but it's totally off the mark, so it is inaccurate and therefore unacceptable. But on the top right, we have the cluster very close to each other and dead on target. This is a system which has got both accuracy as well as precision. The two pictures on the lower half are wholly unacceptable measurement systems because there is absolutely no consistency in the measurement On the left hand side, there is no accuracy. On the right hand side as well, there is no accuracy because the readings are all scattered apart. Now, if we were to look back at the picture on the top left, we see that the mean value of that cluster is away from the true value at the dead center. The difference between the true value at the dead center and the mean value of that cluster is referred to as bias. Now, the bias could come from the instrument, or the bias could come from the analyst. For example, a parallax error that comes from an untrained analyst, and the zero error or the baseline drift that accounts for the instrument's bias or contribution towards bias. Now they have something called sensitivity and discrimination. For them, sensitivity is defined as the smallest difference that the instrument is able to detect and display. So it's something like the least count. Discrimination, on the other hand, refers to the measurement system's ability or usability. For example, if you have a tolerance that says 0.1 mm, the discrimination rule insists that the sensitivity should be at least 1/10 of the tolerance. So if the tolerance is 0.1 mm, then the discrimination should be 0.01 mm. The sensitivity should be greater than 0.01 mm. That is the meaning in which sensitivity and discrimination are used in the other industries. Now let's talk about stability and drift. Drift refers to the change in the accuracy of a measurement system over a period of time. It could be a very small change, but it does happen over a period of time. Now, the smaller the drift, the greater the stability. So we are now talking about the measurement system or the instrument or the gauge, its stability. For example, you have calibrated it today and it has a certain variability about the measurements or the repeatability on the date it is calibrated. Now that variability, if it starts spreading over a period of time, or worse, if the mean value starts shifting or drifting, then it is both losing its repeatability as well as its accuracy. This basically establishes the robustness of the instrument and then will help you determine what should be the periodicity of recalibration. Now please remember, accuracy is compromised very slowly. Accuracy deteriorates slowly, but precision or repeatability can deteriorate very rapidly. So we are talking now that on the date of calibration, we had, let us say, a dispersion or a repeatability which was narrow. Over a period of time, this dispersion starts spreading. That means the repeatability is deteriorating. But if the mean remains exactly where it was, then the accuracy is not compromised. There is no bias being introduced. But if the mean value also starts drifting, then there is a bias being brought into the instrument, and the accuracy is now deteriorating. So we move on to the next point that they worry about, and that is linearity. Now, for us, when we talk about linearity of an analytical method, it means something which we shall take up when we are discussing methods validation. But here, the gauge R&R analysts are talking about the linearity of the bias. In other words, they accept that, okay, fine, if there is a gauge, over a period of time, its accuracy will start deteriorating and the difference between the observed value and the true value will start increasing. They accept that. But they also want to establish that if there is an inherent bias in a gauge, not necessarily over a period of time, but even at a point of time, if it is making a measurement over a range from a low level to a high level, let us say for purposes of discussion, from a level of, let us say, 50 to 150. Fair enough. Now at 50, when you measure, you have a certain observed value and you also have a true value. If you measure the other extreme, that is at 150, it has a certain observed value and it has a certain true value. Now, if there is no bias, then the difference between the observed value and the true value at 50 as well as at 150 would be the same. But if it is not, then is the increase in the bias or the increase between the observed value and the true value, is it increasing linearly or non-linearly? For example, can you say the bias of this instrument can be given by an equation y is equal to mx plus c, where c is the y-intercept and m is the slope of the curve? Can you describe the gauge bias with y is equal to mx plus c? If the bias is fixed, then bias is equal to y equals mx plus c. M is 0 because it's flat and therefore there is c. There's a fixed bias. But assuming it is not fixed, it is increasing. At lower values, the bias is lower. At higher values, the bias is higher. Now, is that change from the low value to the high end value, is that change in the bias uniform? In other words, is there a slope? And if there is a slope, is that line a straight line or non-linear? These are the things that they like to establish. They do not assume that any instrument does not have a bias. They do not assume that the bias is not fixed, that it could vary, and they would like to check whether that variability is linear or non-linear. More importantly, predictable or not predictable. To sum it up quickly, here we have a representation. Measurement is being made over the range 50 to 150, where the true value over the entire range agrees with the observed value. You have no bias. Now, in the second, you see that at both 50 as well as 150 and over the entire range, the offset that is there is 1 unit, and therefore the bias is 1 unit. The difference between the observed value and the true value is 1 unit across the entire range. It's a fixed bias. In the next, you see that you have at the lower end you have 1 unit, and at the upper end you have 4 units, and you have over the entire range the bias increasing linearly. And in the last one, you see that the bias or offset at 50 is 1 unit and at 150 is 10 units, and the entire bias increases exponentially, non-linearly across the range. Now, this is the level to which gauge and R&R experts analyze the dispersion. They talk about the bias, the stability of an instrument, the drift in the instrument, and if there is a drift, whether that drift is fixed or varying linearly across the range or non-linear across the range. And finally, they have something called attribute study. Now, what does that mean? They look at the total environment. Now, in the attribute study, they would include everything except the instrument. For example, analyst to analyst. Different analysts, different instruments, different times of day, different seasons. Whatever variables can be brought in the operational context. This would include things like the environmental temperature, because it's sensitive electronic equipment. Temperature will have an influence on the electronic components. The RH in the environment, the humidity or lack of it will affect the components. If there is humidity, there will be a change in one direction, and if there is no humidity, there will be an increase in the static charges, which could even damage your electronic components. Now, temperature and RH are not the only things they worry about. They look at things like, for example, the interference coming in the electrical supply line. Now, all of you are familiar that if you have a TV and somebody puts on a mixer, then sometimes you get disturbance on the screen. This is called electrical interference, different types, electromagnetic interference, RF interference, whatever. So they like to see whether there is any predictability about the interference in the electrical line, because all the measurements are using electronic instruments which are sensitive to the supply line purity. Supposing somebody were to put on a heater, then the power factor would change because now there is heavy resistive load. Now, if somebody were to put on a centrifuge, so there is an inductive load that is added on, that would again change the power factor. Now, if the power factor changes, how does it affect your instrument? So these are all things that they make an estimate about, factor it in, and then carry out what is called analysis of variance using different replicates at factors at different levels, and so on and so forth. A measurement systems analysis considers the following: selecting the correct measurement and approach, assessing the measuring device, assessing procedures, assessing operators, assessing any measurement interactions, calculating the measurement uncertainty of individual measurement devices and or measurement systems. Common tools and techniques of measurement system analysis include calibration studies, fixed effect analysis of variance, components of variance, attribute related gauge study, gauge repeatability and reproducibility, ANOVA analysis of variance from the gauge repeatability and reproducibility studies. And lastly, there is also an element of destructive testing analysis wherever testing leads to destruction of the test item. Now, we talk about precision and the mutual agreement of readings. And we talk about a mean and a spread around the mean. And the standard deviation, the square root of the variance, is deemed to be an index of the standard error. Whether that is the right word to use or the wrong word to use, we will find out soon. But it is what is called the uncertainty in the measurement. So no measurement is ever valid until and unless it is accompanied with a statement of what is the uncertainty associated with that measurement. Now, what is this uncertainty? Let's try and understand. The uncertainty of a measurement tells us something about its quality. Uncertainty of measurement is the doubt that exists about the result of any measurement. You might think that well-made rulers, clocks and thermometers should be trustworthy and give the right answers. But for every measurement, even the most careful measurement, there is always a margin of doubt. In everyday speech, this might be expressed as give or take. For example, a stick might be 2 meters long, give or take a centimeter. Now, how do you express this uncertainty of measurement? Since there is always a margin of doubt about any measurement, we need to ask how big is the margin and how bad is the doubt. Thus, two numbers are really needed in order to quantify an uncertainty. One is the width of the margin or interval. The other is a confidence level and states how sure we are that the true value is within that margin. Now, what do we mean by that? Now, let's take an example, and we made a certain measurement, and it is, let us say, 20 centimeters is the mean value, and the standard deviation, let us say, is 0.1 centimeter. Now, you would like to say, if asked, how sure are you that it is 20 centimeters? Then you say 20 centimeters, give or take, point that many centimeters. Why do I say that many? It is because the standard deviation by itself is an index that covers by itself only 2/3 of the population. One standard deviation this side and one standard deviation that side covers 68% approximately. Two standard deviations this side and two standards deviation this side covers 95% approximately. 2.575 standard deviations on one side of the mean and 2.575 on the other side of the mean, totality of approximately 5.15 standard deviations covers 99% of the spread. And of course, if you have 3 standard deviations on this side and 3 standard deviations on that side, it is 99.73. In other words, the uncertainty is 0.27%. So, if I were to say the standard deviation is 0.1 centimeter, then I might like to tell you that the measurement is, in my opinion, 20 centimeters plus minus 0.2 centimeters. I can say that with 95% confidence. It is 20 centimeters plus minus 0.2575 centimeters. I can say that with 99% confidence. This is what it means. One is the error component element or the standard deviation, and the other is the coverage. The coverage factor would depend on what is the confidence level with which you wish to speak. The greater the confidence, naturally, the greater the interval of uncertainty or the band of uncertainty. So 20 plus minus 0.2575 is, in my opinion, the value of this measurement. I can say that with 99% confidence. Now here is something very interesting. If there is a dispersion, there are two components to that dispersion. One, which we call the error. That's why I said the word standard error is perhaps a wrong choice to describe that standard deviation. Because that standard deviation has two components. One is an error or a mistake that can be correctable. For example, zero error on the instrument, which gives you that certain bias, is correctable. The calibration certificate gives you something by which you can make that necessary correction. The analyst is very careful to see that he doesn't make a parallax error. So error is something that is correctable. In other contexts, one would say chance variability and assignable variability, or common cause variability and special cause variability. For special cause, there is always an assignable reason. For common cause, there is no direct assignable reason. It is inherent to that particular process. So here we are talking about error as that special cause which can be correctable. The moment you have identified the cause and removed that cause, that part of the variability disappears. So error is that assignable cause or special cause. Uncertainty is that other common cause variability, chance variability, the random variability that is inherent to that particular measurement process. So let's see that described. Error versus uncertainty. It is important not to confuse the terms error and uncertainty. Error is the difference between the measured or observed value and the true value of the thing being measured. But uncertainty is a quantification of the doubt about the measurement result. Whenever possible, we try to correct for any known errors, for example, by applying corrections from calibration certificates, etc. But any error whose value we do not know is a source of uncertainty. If we were to look at it from here, the top left shows a certain error that can be corrected as has been done in the picture on the top right. But that spread that is occurring amongst that cluster, within that cluster, that spread is common cause variability. That is the uncertainty we are talking about. Whenever we talk about calibration, key parameters associated with calibration are accuracy, precision, bias, and uncertainty of measurement. The effects that give rise to uncertainty in measurement can be either random or chance or common cause, where repeating the measurement gives a randomly different result. If so, the more measurements you make and then average, the better estimate you generally can expect to get. The other is systemic, assignable, special cause, where the same influence affects the result for each of the repeated measurements, but you may not be able to tell. In this case, you learn nothing extra just by repeating measurements. The systemic component of uncertainty is contributed by ever so many sources: measuring apparatus, operating procedures, and some inherent drawback of the instrument under calibration. Again, depending upon the pattern followed by these uncertainties, this pattern may be rectangular or normal or Gaussian distribution. Contribution due to each element is separately determinable to arrive at an overall value of systemic uncertainty. The total value of uncertainty is computed based on the values of both random and systemic uncertainties for a given level of confidence. For more about quantifying uncertainty in analytical measurements, you have Eurochem 1995 guide as a reference, as well as this excellent Measurement Good Practice Guide, a beginner's guide to uncertainty of measurement by Stephanie Bell, issue number 2, volume